Okay, let's talk about Biot-Savart, which is the method of last resort when it comes to finding magnetic field. As you can see, this equation is probably one of the ugliest equations that we have encountered in AP Physics C. We've got this mu naught over 4 pi, which is kind of standard in a magnetic field situation. We've got I times dl cross r. So this is the tiny little length vector dl cross producted. I don't think that's a word, but we're going to go with it. The cross product of dl with our radius vector. So the radius vector, it's got the magnitude of the radius multiplied by the direction of the radius, like so. So this is the same value as this. Okay, so we can rewrite this as mu naught times I dl cross r times the unit vector r. So that just is the direction. Okay, all divided by 4 pi r cubed, and we are able to cancel out one of these r's with that cube in the bottom, so this will become a squared. Okay, we got excited. There you go. So a cross product, generally, you are looking for the sign component between the sign component of your radius, right? It's going to be like diagonal. So you're looking for only the perpendicular component of the piece of wire that is carrying the current. So yeah, this is what you come up with. We can write this again for good measure. We integrate, right? So the integral of dB is equal to the integral of mu naught over 4 pi. That's a constant. I could have pulled that out. I is probably also a constant. And so we're left with dl sine theta over r squared. Generally, this is going to be the interesting part. Okay. Explain the difference between these two equations. So the ones that were originally printed, there's not a difference. This one is just simplified a little bit more. We've replaced our radius vector with the magnitude of the vector and the direction of the vector. Okay, so our first sample problem is to calculate the magnetic field around a long straight current carrying wire. Long is code for infinitely long. And this is something that we have done with Ampere's law. We already know the answer to this because of Ampere's law, right? We should be getting mu naught I over 2 pi r as our answer. Okay, so if we want to show Biot-Savart and kind of like the process, okay, we have this wire, it's carrying a current, I don't know, that way. We can think of this wire as the summation of all these tiny little pieces of wire length dl. Okay, so when we integrate, we get the whole entire length, which is going to stretch from negative infinity to positive infinity. So writing the Biot-Savart law, dB is equal to mu naught I dl sine theta over 4 pi r squared. Okay, so I've already kind of talked about like what dl represents. Let's talk about r. We're trying to figure out the strength of the magnetic field at maybe some arbitrary point P, like so. The distance between each tiny little length of wire carrying a current I and P, that is R, right? My radius R pointing in that direction. And we can split R up into X and Y components. Here, this is going to be some distance x, which as we move along, as we look at our different pieces of wire of length dl at these certain locations, this horizontal distance between the wire and the point P, this x is going to be a constant, but this y going vertically is going to be what varies. So I can rewrite this equation, instead of saying dl, I can narrow it down so that only one direction is changing at a time. So mu naught times I times dy over 4 pi, well, Pythagorean theorem, r squared, x squared plus y squared. Okay, so that substitution just from Pythagorean theorem. And then, so sine theta, or rather, we are looking to pick out the component of the radius that is perpendicular to the current, which is going to be this component right here. Okay, so sine theta is going to expand into x over the square root of x squared plus y squared. Okay, that would mean that my angle theta would be right there. Okay, so let me pull out everything that is a constant before I start trying to integrate. So the mu naught is a constant, I is a constant, 4 pi is a constant, okay, dy is going to hang out over here, and then the x is going to be a constant. Okay, divided by, so this x squared plus y squared times the square root of x squared plus y squared ends up being x squared plus y squared to the 3/2 power. Okay, and this is ready to integrate. Yeah, cool. You're going to have to do u substitution here. That's gross. Boo. You can also be kind of cute, kind of cheeky. Instead of going from negative infinity to infinity, you can go from 0 to infinity, but you have to double it. It's cute, right? And then when you do u substitution for this, remember, we already know what we're going to get. All right, we're going to get 2 mu naught I x over 4 pi, and then this integral is going to come out to 1 over x squared. Okay, so we can cancel out a little bit more. So with this 2 and the 4, we'll have a 2 left in the bottom, and then this x and the squared will cancel out, and we're going to be left with mu naught I over 2 pi x, which is the same as what we got with Ampere's law, which is great. Now, between Ampere's law and this nonsense with the trig substitution, and you actually have to do like an integral, yeah, take Ampere's law every single time, okay? Any opportunity you have, you would prefer Ampere's law over Biot-Savart. You are forced into Biot-Savart if your wire is of a finite length. Yeah, it's really gross. I am not going to do it because you won't be asked to do it. You might be asked to set it up, but I really, really doubt that. It's in your book on page 927. Let's see. I've been staring at this page trying to figure out if it's worth it to show y'all, and really I don't think it is. So there's the pictures. We've got this wire here that's a finite length. We've got theta 1, angle theta 2. There's this angle phi. I don't know what they're doing with that. It's kind of gross. But yeah, and it continues on for like a whole entire page, pretty much. And then this is the answer. So mu naught over 4 pi times I over r times the sine of theta 2 minus the sine of theta 1. Yep, lovely. Look at this derivation. There's like a secant squared involved, and like, oh, this is polar. I don't know what's going on. Yeah, it's not worth the effort in trying to figure out how to work that integral. Something that is not so bad, and something that you have to use Biot-Savart for, is if you have a circular loop, a single circular loop. Now we use Ampere's law to do like a whole solenoid, but we kind of cheesed it. We didn't actually figure out what was going on if we just had a plain circular loop of wire that has current flowing through it. And we want to know what the magnetic field is right at the center, okay, right in the middle of that. And although Biot-Savart looks scary, it's actually not that bad. It's still a pretty highly symmetric case. Ampere's law doesn't work because you can't draw an Amperian loop so that the magnetic field would be the same at every single point on the Amperian loop. It's kind of the same constraints with Gauss's law. When you draw your Gaussian surface, you want the electric field to be the same at all points on the Gaussian surface. Here, when we draw our Amperian loop, the magnetic field is going to be different on the inside of the wire than on the outside of the wire. And that is why we are forced into using Biot-Savart here, but we will find this symmetry makes it not the absolute worst. So mu naught I times dl sine theta all over 4 pi r squared. I don't think I forgot anything this time. Okay. So each little piece of wire, dl, right, so going that way, is dl. Our radius is, oh, look at that beautiful angle. It's always going to be 90 degrees. So this is going to just be 1. Okay. The distance between each little current carrying wire bit dl and the point of interest, right smack dab in the middle of that loop, is actually going to be a constant, which is great. So capital R squared in the denominator there. And so looking at this, mu naught is a constant, I is a constant, dl, well, that's what we're integrating with respect to. The 4 is a constant, pi is a constant, the capital R is a constant. So this integral actually turns out to be really easy. We can pull everything except for the dl outside of our integral sign. And then we just have the integral of dl. Well, we want to go all the way around, right, our wires. So our bounds on our integral, we're going to go from 0 all the way to 2 pi r. All right, we're looking for the whole circumference of the wire. It's not too bad. You can imagine if we had only a semicircle, your bounds would change, right? If it was only a half circle, instead of going 2 pi r, you just go pi r, okay, for 1/2 of that. Definitely have seen that before in setting up a free response question. This, though, is a very easy integral to evaluate for once. Mu naught I over 4 pi r squared times 2 pi r. Boop. We can cancel some stuff out. The 2 pi, let's see, that turns into a 2. This r cancels out with the squared in the denominator, and we come up with, so let's see, mu naught I over 2r. Yay! So that's what's up for a single loop of wire. You can imagine if we actually had a solenoid, all right, you pop an N in there for the number of coils that you have. Cool. All right, last thing, I already mentioned Gauss's law for magnetism on the last set of notes, but here it is again. It just bears repeating. It's pretty straightforward. Gauss's law for electricity, just as a comparison, right? E dot dA is equal to Q enclosed over epsilon. This was super useful whenever we made a Gaussian surface that was set up so that the electric field was constant every time. This whole integral just kind of poof, disappeared, and it's not actually an integral at all. It's like a geometry thing. For magnetism, Gauss's law specifically is about Gaussian surfaces, which means they're 3D. It is the dot product of B dot dA. So for electric field, we summed the discrete charges here. When magnetic fields are created, right, they're caused by moving charges. There's always like a front side and a back side of a charge. You can't cut apart like the front side and the back side. So there's not such a thing, there's not an equivalent for magnetism like there is an equivalent for charge. Or I guess it would be a pull of a magnet, but you can't have one without the other. The implication here is that you can't have a charge that is cut in half. All right, there's one side moving forward, one side moving backwards, always, or not backwards, sorry. There is a leading side and there is a trailing side, always. And the implication of this is that there are no magnetic monopoles. You could, if you wanted, have a single proton just chilling, creating that outward electric field. You cannot say the same for a magnetic pole. Anytime you have a north magnetic pole, there is also a south magnetic pole.